Okay. Welcome, everyone. Today is May 1st, which is the start of Volcano Awareness Month in Washington. So we are very excited to have you here for our annual State of the Cascades presentation brought to you by the U.S. Geological Survey Cascades Volcano Observatory. I'm also going to put in the chat a link to our press release, which is also a description of some of the events that are upcoming this month. We like this as an opportunity for everyone to learn about our 5 active volcanoes in Washington, about the volcanoes in the Cascades, the science behind them, the history, their hazards, and how you can prepare for them. So please feel free to check out all these events. They're all open to the public. Just some opportunities for you to learn about this amazing state we have and all the volcanoes possible. So I would like to hand this over to John Major, who is the scientist in charge at Cascades Volcano Observatory, to tell us a little bit more about our volcanoes. Go ahead, John.
All right, thanks, Brian. Let's try to get the screen shared here. So let's see, I'll try that one. And maybe that's not the one. Let's find out here. Give me a second. And one. Do you see what looks like a normal PowerPoint?
That looks like a presentation.
Okay, great. I've got it in triplicate here. So excuse me, I can't see any of you. So if there are any questions, maybe we can hold them to the end, or if there's any reason, Brian, you'll just have to let me know that something's popped up. So welcome. What I thought I'd do today is start off the talk. I don't know who's all in the audience. I don't know how familiar people are with volcanoes and volcano hazards and volcano processes. So I thought what I'd do is I'd begin the talk. First part of the talk, we'll talk a little bit about what are the hazardous processes at our Cascades volcanoes. I mean, what are the things we kind of worry about? What are the things that can cause complications and harm to society? And after we step through that, then I'll give you a brief update on things, some of what's been going on at some of our Cascades volcanoes over the past year or so. Excuse me. All right, so go ahead and start. So I think most of you know that the Cascade Range is home to many volcanoes and volcanic fields. We have these, as Brian's kind of alluded to, just these beautifully charismatic landforms. But these are very geologically active landforms. And this is just a cartoon that shows eruptions or eruptive activity that's been deduced over the past 4,000 years at each of our volcanoes in the Cascades. And this is obviously more than just the Washington Cascades. So you can see, first of all, from this cartoon that the frequency of activity is very unevenly distributed. Some volcanoes have been pretty quiet the past 4,000 years, and some of them have been extremely active the past 4,000 years. But if you just look at the last 1,000 years, you can see that quite a few of our volcanoes have had some form of activity. So these are not just dormant, morphologic features sitting on the landscape. They are geologically active volcanoes. And if we average over, say, the last 10,000 to 12,000 years, and I'll talk about what that asterisk means in just a second, our large stratovolcanoes that we see perched on the landscape experience maybe a couple eruptions per century. But it's very common that if one of them does go into a period of unrest and eruption, that those eruptions can kind of come in bunches. And, harken back to Mount St. Helens in 1980, it had its big cataclysmic eruption on May 18th of 1980, but then through the summer of 1980, it had a number of eruptions. Again, in 2004 to 2008, it had another eruption. So they can kind of come in bunches once they do go into a state of activity. Now, when you talk about maybe a couple eruptions per century in the Cascades, is that really significant over a single human lifetime? It's very possible that someone born in Washington can live their entire life in Washington and never experience or never witness an eruption in the Cascades. But if you're an emergency management planner or a land use planner, and you're thinking over generational time frames and plant those kinds of planning horizons, then even something that's fairly low frequency is something you do have to give some consideration to and think about. The caveat here that I want to point out is that this cartoon is really, and the statistics are really only for the large stratovolcanoes, and they don't include eruptions of what we call distributed volcanic fields. These are these cinder cones and lava flow fields, such as Indian Heaven, for example, that sits between Mount St. Helens and Mount Adams, or down in the Cascades. These are also volcanic fields that periodically are active, but those are not accounted for in this cartoon or in those statistics. But at the large stratovolcanoes, the probability of eruptions are low, but they are very high consequence type events when they do happen. So what do I mean? What happens when a volcano is geologically active? What are we talking about? So the next several slides, we'll talk a little bit about volcano processes and volcano hazards. So at a volcano, there are lots of things that can happen during an eruption. You can get all kinds of cascading events. You can get like single events that happen, and not necessarily all these things happen at once, or sometimes an eruption will happen and all kinds of these things can happen. So we can kind of very broadly bin the volcano hazards into two general categories. Those are the things that flow away from volcanoes, and these are the things that fall out of the sky. And the impacts generally depend on time and distance from a volcano. So, for example, let's say we're within the areas within maybe 20 miles of a volcano, kind of a rough number. Multiple things can affect the landscape within about 20 miles of a volcano, and those things can happen within minutes to hours. As we move further away from a volcano, for example, let's look at some river channels. Volcanic mud flows, which we call lahars, they can affect valleys, and these large volcanic mud flows, lahars, can travel many, many tens of miles downstream, and they may affect areas downstream, say within tens of minutes to several hours. The next is volcanic ashfall, which volcanologists call tephra fall. This can affect areas tens to hundreds of miles away from the volcano as that material gets carried downwind. And areas that far downwind, it's going to take hours before this can really affect those places. And then in the aftermath of volcanic eruptions, there's a lot of loose material on the landscape. And so Mother Nature likes to erode all that material and flush it down river systems. And so excess sediment in watersheds can make river channels that drain volcanoes very unstable. And sometimes that instability can last for years or even decades. And then one other thing I'm going to call your attention to is this little box down in the lower part of this cartoon. And it basically says that most of our volcano hazards are associated with eruptions, but there are some hazards, such as very large volcanic mud flows or what we call debris avalanches. These are large landslides, and we'll talk about this in a little bit. Those can happen even in the absence of an eruption. So you don't have to have an eruption to have some of these processes occur. So let's step through some of the major ones in the Cascades that are the ones that really pose particular threats to society. They're the big hazards that we worry about here in the Cascades. And the first one I'll start out with is what we call a debris avalanche. This is like a very large landslide. The quintessential one, not only in the Cascades, but worldwide, is Mount St. Helens in 1980, where the entire north flank of the volcano collapsed in this gigantic landslide. So these are landslides that they're composed of rock and water and glacier ice and soil and vegetation and anything that they can erode as they move down slope. They represent very large failures of the flank of a volcano. These can be enormous in size. They can remove very enormous volumes from a volcano, and they can deposit. They deposit the deposit from these landslides can deeply smother river valleys. And many of you, I think, have probably been to Mount St. Helens. You've probably been up the North Fork Toutle River to the overlooks, and everything you're looking out there, a large part of what you see in that upper North Fork Valley is the deposit of this very large landslide. So it can really deeply smother valleys. And if this material happens to be particularly wet at the time it fails, or particularly clay rich and gooey, it can actually transition directly into a large volcanic mud flow that can flow very far down valley. And in the Cascades, the kind of the quintessential example of that is what we call the Osceola mud flow from Mount Rainier that happened about 5,600 years ago. Um, Basically, the east southeast flank of Mount Rainier collapsed very much like this, and it was composed of enough gooey material and wet enough that it very rapidly transitioned into a very large mud flow, a very large lahar that went all the way down through the White River Valley and on into the Puget Sound lowlands. So this can be a particularly hazardous phenomena, and just to kind of give you a little more sense of what this is like rather than just sort of looking at a still photo. We're going to play a movie, kind of a time-lapse movie that's been morphed together from these photographs. So hopefully this will work. So what you can see from that time-lapse movie is that not only do we have this large landslide off the volcano, but you can see that it triggered this whole cascading series of events. And we'll talk a little bit more about what some of those processes are. So the next process we'll talk about is what volcanologists will call a pyroclastic flow or a pyroclastic surge, or kind of more generally, we will call these things pyroclastic density currents. These are dry avalanches of hot rock and gas. And in that movie there, and you see the photograph in the lower left, this is material that can rush down the size of a volcano extremely fast, like 60 miles an hour or more. These can form in a variety of ways. At Mount St. Helens, that particular process early in the morning on May 18th of 1980 formed when that large landslide basically reduced all the pressure that was on the magmatic body that had pushed up into the volcano. That reduction in pressure released a lot of the volatiles, a lot of the gases that were trapped in that magmatic system. It exploded out across the landscape, and it formed this incredibly large, very fast moving pyroclastic density current that swept along the landscape. And you've probably heard that referred to as the lateral blast from Mount St. Helens. Another way these things can form, a good example is in that upper right-hand photograph at my own volcano, where you'll get the volcanic eruption plume that gets ejected up into the atmosphere. And if that material is not sufficiently buoyant, those particles will collapse back down to the ground and then rush down the slopes of a volcano as pyroclastic flows that you see in these images. And again, just to give you a little sense of what these are like, here's some movie footage that was compiled by the International Volcanological Community, and we'll hopefully play this. So there's no audio with this one, but here's an example of material that gets ejected up, thrown up into the atmosphere. It's pretty denser than the atmosphere. It doesn't get buoyant, collapses back down, and you can see that as it collapses back down, it forms these very fast-moving flows. Here's one where a lava dome, the front of a lava dome, happens to collapse, and it very quickly disintegrates and transitions into one of these pyroclastic flows. Um, And these are incredibly deadly. There's no way you're going to outrun this thing. There's no way you're going to outdrive this thing. So fortunately, these tend to affect areas relatively close to volcanoes. Little cartoons just kind of showing you relative speeds here. So these are, Mount St. Helens was a bit of an exception. That lateral blast at Mount St. Helens swept broadly across the landscape, but most of these things are going to be restricted fairly close to the volcanoes. But if they happen to melt snow and ice on a volcano, they can form one of these volcanic mud flows or lahars. So they can trigger a bunch of other processes as well. Again, these cascading effects. I've mentioned to you now volcanic mudflow, or what we call lahar. These are, think of slurries of rock and sand, mud, water, debris. Um, to try to give you a little more of a picture of it, think of a river that has the consistency of a soupy milkshake with large chunks in it, or wet cement. If you've ever gone to Home Depot and bought bags of cement to put your fence posts in your yard, you pour that in your wheelbarrow and you mix it with a little water and you make this nice soupy slurry. That's kind of what a volcanic mud flow looks like. So they follow valleys that drain away from volcanoes. They can range in size from something that's not really small, barely going to get off the flank of a volcano, to something like the Osceola mudflow that I told you went all the way from Mount Rainier all the way down to the Puget lowlands. And they can form in a whole variety of ways by melting of snow. They can form by rainfall. They can form by if a large debris avalanche happens to is wet enough and transitions directly into one of these things. So this is one of the biggest hazards here in the Cascades. This is one of the ones we really worry about. And just to give you a sense of one, if you've never seen a debris flow or a small lahar, this is some movie footage from a volcano in Indonesia. There's audio. The audio is in French, and one of these days I'll have to ask my friend Franck, who provided this to me, what he's saying. But this will give you a little bit of a sense of what one of these looks like. And what I want you to see when I play this video is I want you to pay attention to kind of how fast this is moving, and I want you to pay attention to the size of the material that's it's moving. And when it passes the photographer's point, you'll get a sense of how deep it is. And this is a pretty small one. Okay, so hopefully you get a sense that these are pretty powerful. They're more than just your typical river flood, right? You can see the consistency of this. You can see the size of material it's moving, how fast it's moving. And as I mentioned, in this case, this is relatively small. Um, oops, before I go on to the volcanic ashfall, um, at Mount St. Helens, unfortunately I didn't put this slide in, but there's a photograph of a person standing next to a tree in the Toutle River Valley at Mount St. Helens back in 1980, and the person's like 6 foot plus tall, and you can see the mud line on the tree, and that mud line is probably 5 times as high as that person is tall. The mud line's at least 30 or 40 feet up on the tree. So imagine a river of what you just saw, 30, 40, 50 feet deep, coming down the river valley. So it gives you a sense of kind of the power and the real hazard that that poses. What you just in that movie you just saw, imagine now you were at Mount Rainier 5,600 years ago, and the Osceola mudflow is coming down the river and close to the volcano, kind of up in the the Sunrise area and down the White River, close to the volcano. That material is like 100 feet deep. So imagine something 100 feet deep like that, roaring down the valley. And I hope it gives you an idea of the kind of hazard that that particular process poses. Another one we worry then about in the Cascades and volcanoes worldwide is we call tephra or volcanic ashfall. And I'll play this movie while it's going. Volcanic ashfall represents shattered fragments that are carried downwind by volcanic plumes. And this ash it consists of sharp fragments of rock and minerals and broken glass. If the particles are less than about 2 millimeters in size, that's what we call volcanic ash. If they're larger than 2 millimeters in size, we've got some other names for them. But this is basically what volcanic ash is. It's fragmented rock, minerals, and glass particles. It gets ejected high into the atmosphere and then carried downwind, as you can see in these photographs in this movie. And as that material, that's the material that can affect communities, hundreds of miles downwind. Generally, it's not going to present um, a direct sort of, you know, it's not going to directly cause hazards to people. It's not going to kill people, but it is really a nuisance. It can be a real problem with aircraft. If a jet engine happens to ingest that volcanic ash, that's a real problem. That's happened a few times and almost caused some plane crashes. Um, but it can short out electrical systems. It can make roads very slippery. It reduces visibility. If people already have pulmonary issues, breathing that stuff in is not very good. Remember, it's broken fragments of rock and glass and minerals, so it can cause some real health problems. But unlike a Lahar, it's not going to like mow your house down or anything like that. Another hazard here in the Cascades that we worry about a bit are lava flows and lava domes. Lava flows are generally pretty fluid for the most part. They represent rivers of lava that can pave large areas away from a volcano. Um, in the Cascades, we don't tend to have volcanoes that erupt too much of the really fluid lava like we have over in Kilauea volcano in Hawaii. But we do have lava flows that at least move, several miles, can move several miles away from a volcano. If the if the viscosity of the lava that emerges is more viscous, then rather than flowing away from a volcano, the material tends to pile up around the eruptive vent. And the photograph on the right is a picture of the crater of Mount St. Helens, and you can see some of the lava domes that formed as material emerged to the surface, but wasn't fluid enough to flow far away, and it just tended to pile around the vent. And just to give you a sense of what some of these look like, the video on the right is from Kilauea in 2018. And so this is very fluid basaltic lava. Um, Occasionally, some of our Cascade volcanoes will erupt material like this. About 1,800 years ago, Mount St. Helens erupted very fluid basaltic lava. If you've ever visited Ape Caves at Mount St. Helens, it's formed by this very fluid basaltic lava. So some of these what I call these distributed volcanic fields, sort of like Indian Heaven, places like that, they tend to be a bit more of this basaltic lava. So if you had a fissure open up and a bunch of lava began to come out of the ground in those distributed volcanic fields, it'd probably be a bit more like that. More likely to happen, or more generally, what happens at our Cascade volcanoes is that our lavas are more viscous, and so they tend to form domes around the vent. And this is just a kind of a morph set of what we call digital elevation models showing you changes at Mount St. Helens as the lava dome from 2004 to 2008 grew. And so you can see how it kind of piles up around the vent. And in this case, it tended to squish the glacier ice that was in the crater, pushed it around, and actually you can see the arms of the glacier advance as the ice got kind of squeezed and pushed around a little bit. But those lava domes pile up around the vents. And as you saw in some of the earlier footage, then you can actually, if the parts of those lava domes collapse, they can form pyroclastic flows. So that can be a big hazard. And then I mentioned earlier that volcanic eruptions, these explosive eruptions will dump lots of sediment on the landscape from pyroclastic flows, debris avalanches, lahars, volcanic ashfall. All that sediment is very easily eroded, and it tends to get flushed downstream, and it causes all kinds of problems further downstream as that material gets flushed through the river systems. And so the principal sources for the sediment, as I mentioned, are going to be the volcanic ashfall in the landscape, landslides. And I'll call your attention to the upper right-hand photograph. It's a photograph of Mount Pinatubo in the Philippines from 1991. You see that little rock island in the Sea of Tan. Well, all that tan material is pyroclastic flow deposit that was deposited during the eruption of Mount Pinatubo. And I want you to pay attention to that little rock knob that's sitting there in the midst of all that, because a couple of years later, you see that rock knob again, and you can see all the erosion that took place. So tremendous amounts of erosion at Mount Pinatubo. That it was very easily eroded material. The photograph on the left on the top at Mount St. Helens, it's kind of like this is a view from hovering in a helicopter, roughly at about the southwest shore of Spirit Lake. So ballpark there. You're looking downstream. This is a photograph from 1980, so you can see all the very chaotic deposit, which is the large landslide, the debris avalanche at Mount St. Helens. And then several years later, this is roughly the same spot. You can see all the erosion that took place. And then in the middle column at the top, black and white photo of Mount St. Helens looking upriver of the upper North Fork Toutle River. All that material in the foreground in the valley is the large debris avalanche deposit, and then kind of similar type view in the early 90s. You can see all the erosion that took place in the channel development. So lots of material gets eroded and gets flushed downstream. All that material moving downstream can fill the channels downstream, which causes loss of flood protection as all this material accumulates on the channel bed. It can actually cause channels to divert. The upper right-hand photograph is from Chaitén volcano in Chile, and you can see the channel coming down. Over on the right-hand side of the image, the channel actually filled up, and it caused the river to divert through the middle of a small town there. The lower right-hand photograph is actually from the Sandy River at Mount Hood. This is all the sediment that accumulated in the lower Sandy River following one of the last eruptions of Mount Hood back in the late 1700s. So lots and lots of sediment gets moved downstream and can cause all kinds of problems. In fact, at Mount St. Helens, here we are 45 years after the 1980 eruption, and society is still dealing with the sediment that's flushing down the Toutle River system. So now that you know a little bit about processes, I'm going to tell you a little bit about who we are. So we are the USGS Cascades Volcano Observatory. Our mission is to provide volcano hazard assessments and to detect unrest and give timely warnings about volcanic activity, and work with folks like you to ensure that your communities are volcano ready and hopefully safe the next time one of the volcanoes awakens. Our area of responsibility is Washington, Oregon, and even over into Idaho, and we assist other observatories as needed. We're one of 5 volcano observatories within the USGS Volcano Hazard Program. We have over 80 people at our observatory, and you can see we're very broadly disciplinary. We have all kinds of geology, geophysics, hydrologists, geochemists, field engineering specialists, instrumentation specialists, IT, electronics. We have mathematicians on our staff that help develop sophisticated models that we can use to make predictions of various hazards. And we also, some of the staff here are part of what we call our Volcano Disaster Assistance Program. It's a program that's funded by USAID that can provide assistance overseas to countries that are suffering volcano crises. So pretty broadly interdisciplinary here. We touch upon all kinds of topics, and all these topics are really relevant to all the myriad of things that can happen at our volcanoes. At CVO and at our other observatories, our core, we have kind of 3 core functions. One core function is research. So we study the histories of these volcanoes. How often do they erupt? How frequently do they erupt? We study the processes that we just looked at. We've developed a couple of very sophisticated models for predicting how fast, how far large volcanic mud flows can advance down river valleys, and also another one that can predict if we know something about how much ash is being injected into the air, and we know something about the wind trajectory patterns, we can predict where ashfall, volcanic ashfall, is going to drift downwind, and actually how much will be depositing out at various distances from the volcanoes. Another thing we do here at the observatory, another part of our mission, is to monitor our volcanoes. So we have lots of ground-based monitoring, and we do some space-based monitoring. So we try to keep up on the state of health of the volcanoes by monitoring them in a variety of ways. And then we have all our community preparedness, public outreach, public engagement. So We've helped develop response plans. We have a lot of educational resources, hazard products. We're active on social media. We participate and help run tabletop exercises. So these are kind of the three functions within our core mission. So I'll talk a little bit more. I'm going to focus a little bit more of the rest of this talk on some of our monitoring. So as magma moves to the surface, it has to break a pathway. And when it breaks that pathway, it's going to generate earthquakes. As magma gets closer to the surface, the gases that are trapped within that magma are generally going to get released as the pressure reduces on that magmatic body. And the three primary gases that are released are water, CO2, and SO2. And so we monitor for CO2 and SO2. That can tell us something about maybe how close the magma might be to the surface, whether the unrest that we might be seeing is actually related to magmatic movement. And then as magma moves closer to the surface, it's going to increase pressure on the ground surface, and it's going to cause some very detectable changes on the ground surface. We call that ground deformation. And that ground deformation can be pretty subtle. I mean, it might be only a few centimeters, maybe a couple inches, or it can be really obvious, but we have a variety of ways of detecting that. So these are the three primary things we monitor for. And we do this through a variety of ways. We have lots of tools and techniques to kind of look for magma on the move and tracking it over time. We use for earthquakes, we've got a suite of seismometers distributed across the landscape to detect the earthquakes. We use GPS technologies to look at ground deformation, and we can also monitor ground deformation from satellites in space. We monitor gases generally from airborne systems. We can mount instruments in airplanes and fly around. On a few of our volcanoes, we actually have stations that are capable of detecting volcanic gases. So we throw a variety of techniques in our monitoring toolkit to be able to pay attention and monitor these volcanoes. Just a slide. So across the Cascades, we have lots of instrumentation basically across the Cascades is the point of this slide. So, but I'll call your attention to Mount Baker, Mount Glacier Peak, and Mount Adams, the three that are underlined there. And you'll notice that the numbers of instruments on those volcanoes is far behind the numbers of instruments on the other volcanoes. And we are actively making plans and working to try to increase and build out our networks there as well. The other thing I'll call attention to is we partner with the Pacific Northwest Seismic Network, PNSN. They have seismometers distributed all across the landscape in the Pacific Northwest as part of the earthquake early warning system. Some of their seismometers are actually located on the volcanoes or very close to the volcanoes. So we're able to leverage their instrumentation as well as our own instrumentation to be able to monitor the volcanoes. And all the data that are collected from all these different instruments is then fed back to our observatory where we can pay attention to it. All right, so with all that, let's take a little tour through the Cascades here and talk a little bit about kind of what's been going on with some of these, if anything. And so we'll start with Mount Baker in the north. And I'll start out by saying there's no unusual activity going on at Mount Baker. On occasion, if the atmospheric conditions are right, people will observe a little bit of steam, generally comes from the Sherman Crater area. We have been working on a new Lahar hazard assessment. And that hazard assessment has been completed using some next generation assessment tools. And the little movie that's playing down there in the lower right hand corner there is it's a simulation of a large Lahar from Mount Baker. And that model will predict how fast that material gets down valley, how deep it will be at different places. So this is the kind of information that emergency managers can use. It's actionable information. Should Mount Baker go into a state of unrest and produce one of these large lahars, at least right now gives you a sense of kind of where it would go, how fast it might get to your community, how deep it might be, depending on how large the source area is. That report has been through all the approval processes. It's currently in final layout, and we're hoping that that's going to be released probably within a month or so. We're hoping by the end of May for sure, maybe end of June, but that'll be hitting the streets here pretty soon. I mentioned in that earlier slide that Mount Baker is one of the volcanoes that's inadequately monitored. There's very little. PNSN has a few seismometers in the area. And we're right now in the process of finalizing some site selections to be able to expand our monitoring network. Once we get some of those site selections finalized, we will prepare our permit application to submit to the Forest Service, and we're hoping to maybe be able to put out maybe 6 or 8 sites sometime over the coming years. Glacier Peak, no unusual activity at Glacier Peak. Things are relatively quiet there. Again, Glacier Peak is another one of those volcanoes. It's inadequately monitored. It has one seismometer, a PNSN seismometer that's located on the west side of the volcano. PNSN upgraded that site last summer, so it's now got more modern technology at that site. U.S. Forest Service approved us to install 4 new station sites in the wilderness area around the volcano. And we are now working through some installation logistics, and we're hoping to target installing some of those sites starting in 2026. We also have active and ongoing research on the geologic history and processes of Glacier Peak. Mount Rainier. We'll talk a little bit about earthquakes at Mount Rainier. So small earthquakes are common. They happen almost all the time. Back in December, we had a minor swarm at Mount Rainier. We were getting about 10 earthquakes a day for a few days. The maximum magnitude earthquake was about a magnitude 2, and they were generally located right at about sea level or maybe a mile and a half or so below sea level, so they were not up in the volcano. The sizes and depths of the earthquakes in this swarm were consistent with past swarms that have occurred at Mount Rainier. The last time we had a magnitude 2 or larger earthquake at Rainier was almost 3 years ago. It was in 2022. There was no associated deformation with that swarm of earthquakes, so we weren't too worried about magma being pushed up into the volcano. There was no indication that magma was involved. But one of the things that does happen at Mount Rainier are snow avalanches, and our seismic system, our earthquake, our seismometers around the volcano are very good at detecting these, and we can use we can look at which sites are picking up different signals. We can look at the frequency of the signal. And our seismologists can use that information to kind of determine, okay, that's not volcanic earthquakes. That's actually a snow avalanche that's occurring. So by looking at the character of the earthquakes, the distribution of the earthquakes, the stations that they're showing up on, we get a pretty good handle of kind of what's going on when we do get these earthquakes at our volcanoes. At Mount Rainier, we have built out what we call a dedicated Lahar detection system. It's largely on the western side of the volcano. I mentioned to you that about 5,600 years ago, there was a very large volcanic mudflow called the Osceola mudflow that was related to a very large debris avalanche off Mount Rainier that went all the way down the White River. About 500-ish years ago, ballpark, there was a landslide off the western side in the upper Sunset Amphitheater area. That one did not seem to be, as far as we can tell right now, there's no definitive evidence that it was related to any sort of eruption of the volcano. So there's weakened rock up at the summit. Best guess is that some weakened rock failed for whatever reason, formed a mud flow that went down through the Puyallup system and got all the way down to Sumner and Puyallup. It was called the electron mud flow. So we've built out a dedicated Lahar detection system for an event like that. Next time any of our volcanoes go into a state of volcanic unrest, Lahar should be on everybody's radar. But this one that sometimes people call a no-notice Lahar because it does not appear to have been associated with an eruption. That's what this system is meant to try to detect and provide some early insight on. So in the Puyallup and upper Nisqually River, we have completed the installation of our stations there. We still have a couple of stations we want to put along the White River, not because we're worried about a no-notice Lahar along the White River, but more for just situational awareness. Should Rainier go into a state of unrest, Lahars are often shed by Mount Rainier, so this just helps us build out some situational awareness if anything happened to be going down the White River Valley. Um, we use these stations are largely consist largely of seismic and what we call infrasound, sound wave uh, detection. And by using both of those, we can provide more precise information about locations and timing and relative vigor of an event. And the little movie here, this helps lead us to an improved early hazard notification. And this movie is just kind of showing you an example of what one of those stations looks like. So this is one of our field crews is out installing this. So it's a pretty small footprint on the landscape, but provides some incredibly important data for us to be able to provide the earliest possible notification should a Lahar be coming down a valley. Okay, moving on to Mount Adams. Last September, we had a minor uptick in seismicity at Mount Adams, and it lasted from September to about roughly December. Normally, Mount Adams will get a locatable earthquake about every 2 or 3 years, whereas at Mount St. Helens, we might get 10 or 20 a day. So this was, this is sort of typical background for Mount Adams, an earthquake every couple of years. In September, we had 6 that were located, but they were pretty small. They range from about magnitude 0.9 to 2.0. And then we had 2 more in October and November of 2024. They were both pretty small earthquakes. There were also some much smaller ones that were occurring, but too small to locate. So in response, we put out 3 temporary monitoring stations, one of them being in this picture. And of those 3 temporary stations that we installed, one of them is still running. One of them ran out of power. Another one we've pulled. And of course, as soon as we put the stations out, everything kind of shut down and the mountain went quiet again. But we were able to at least collect some data that helps us try to better understand kind of what Mount Adams is capable of doing, what Mount Adams does. So that this just adds to our fundamental understanding of kind of what this volcano can be doing, because we want to really understand what's sort of typical background level. Um, uh, Again, Mount Adams is one of the volcanoes that's rather it's not monitored very well. PNSN prior to those stations we put out, PNSN had 1 station within about 7 miles of the volcano. Lahars are a bit of a concern at Mount Adams. We've had a few over the last like 6,000 years. There have been 2 Lahars that have come off the western face of Mount Adams and made it down as far as Trout Lake or a bit beyond. We are in the process now of doing a new Lahar model for Mount Adams. You remember back at Mount Baker, I had that kind of video image showing you kind of a simulation of a large Lahar at Mount Baker. We're in the process of doing some of that work now for Mount Adams, just to see where Lahars can go, how fast they could go, and how big they might be, depending on how large the volume was at the volcano. We have been approved to install 4 new station sites at Mount Adams. And this summer, we are targeting to install at least 2 of those new permanent sites at Mount Adams. So we're slowly building out a bit of a network at Mount Adams. Progress, takes time to get approval for all these, but we've now been approved for those sites, and we'll start to get those built out this summer. Moving on to Mount St. Helens, earthquakes and earthquake swarms continue to happen episodically at Mount St. Helens. And what's kind of interesting is that when you compare some of the signals we see at Mount St. Helens to patterns in the past, they seem to be indicative of kind of slow magmatic recharge at depth again at Mount St. Helens. Doesn't mean the volcano is going to erupt anytime soon, but there is some indication that the magmatic system is slowly recharging, and Mount St. Helens is most likely going to be the volcano that we see erupt again. We've also done some work assessing potential breach of Spirit Lake. There was some work that was done in the early 1980s. We're kind of revisiting that work with new modern technologies and new modern tools. The idea being that if Spirit Lake was to breach, how fast is the flood wave and the Lahar that it would likely generate? How fast will it get down to the lower Cowlitz system where the communities are located? How deep will it be? So we've done a lot of new assessment of that. The report of that's in final review, and we're expecting that that report will be coming out sometime this summer. And then I'll just call your attention to the fact that on May 10th, CVO is going to host an open house. So if you happen to be in our area that day, it's a Saturday, feel free to stop in between 10 a.m. and 4 p.m. I'm going to step over to Oregon a little bit, just to bring you up to date on a couple things going on in Oregon. So, back at Mount Hood, we had an earthquake swarm in April. We had pretty small magnitude, maximum was about 1.8. We had over 175 earthquakes detected. 96 of those were located 3 or 4 miles below sea level. They were all clustered to the south of the summit, and such earthquake swarms have occurred before. We had one in September 22, June and December of 2023. There's no associated deformation with these, so all these are consistent with moving along some existing faults that Mount Hood happens to sit across. And we have a geologic map that's nearing review, so hopefully we'll be getting that into review pretty soon. And then down at Newberry Volcano, some geothermal drilling and well stimulation has been going on intermittently since December of 2024. And there's been a little bit of minor seismicity that we've detected on our monitoring network, nothing significant. So I'm just going to wrap up a little bit here. The goal for us is to be able to provide effective volcanic crisis management. And that's going to rely on research, monitoring, functioning partnerships, and public engagement. So we've got to have a good monitoring network to be able to help you manage any volcanic crisis. We have to have the research to be able to correctly interpret the data that's coming in from our network. We want to be able to provide you actionable forecasts, and that requires some combination of our monitoring and interpretation of our monitoring data. And then that actionable forecast is only good if we have a functioning partnership between us and you as the emergency managers. So we've got to have that trust built. And then you have to have an educated and a prepared at-risk public. And hopefully a lot of the information that we help push out and our partnering and public engagement is helping prepare and educate the public that's at risk. So in summary, I'd say we have a pretty good handle on the hazards at each volcano. Most of our volcanoes are fortunately remote. The biggest hazards here in the Cascades are Lahars to the west of the Cascade crest. All the rivers eventually bend back to the west. And then volcanic ashfall is the biggest hazard to the communities to the east of the volcanoes, to the east of the Cascade crests. So some of our volcano processes, Lahars and ashfall, can expose large populations to hazards. But we continue to vigilantly monitor the volcanoes. We're expanding our monitoring footprint. We're enhancing our modeling capabilities, and we're gaining a better knowledge about the nuances of volcanic histories and behaviors. And where can you get information? So I highly recommend people interested to subscribe to our volcano notification service, which you can do at this link here. All the volcano observatories we post weekly updates. Alaska and Hawaii are doing somewhat more frequent updates because they've got some unrest going on over there. So this is a place where we post a lot of information and send out notifications. Then there's also our CVO website. We're also active on social media, Facebook, Twitter, and Instagram, and we often push out lots of information there. So with that, I'm going to stop sharing my screen and happy to entertain any questions that people might have.
Thank you very much, John. And we've been getting a number of questions in the chat and some good lively discussion. So I'm going to sort of facilitate that. But overall, thank you so much for coming in and telling us about our volcanoes here in Washington.
Sure.
So we've got a lot of good ones, and I'm going to try to break into some of them. Gail is our famous question asker, if you have not been here, but she always has good ones. So, so I'm going to start out with one of hers. How strong does the wind have to blow to impact the plume, and where the ash and tephra fall?
Yeah, I mean, if the wind is not very strong, you'll get kind of this weakly drifting plume. The biggest particles will fall out very close to the volcano, and maybe some of the really fine stuff could drift far downwind. But if it's not a very strong wind, they're not going to drift very far. If you have a pretty strong wind, that can carry these plumes, hundreds or thousands of miles downwind.
Thank you. It really depends on the wind. Cassidy had a couple questions about the current Glacier Peak monitoring upgrade status, which you may have answered, but would you mind going back to that really quick?
Oh yeah, so the PNSN has a station on the western side of Glacier Peak. Right now, that's the only station around Glacier Peak. And so last summer, they replaced an old analog seismic system with new digital broadband seismometers. So they did some upgrades. I can't remember. They were going to try to put in a GPS sensor. I can't remember if they got that in or not, but I know they at least got the seismic part upgraded for sure.
Thank you for that. Okay, we got a question off chat that was we were trying to learn. Sam wanted to know more about how interconnected the stations are, and as emergency managers, we're curious if they would be vulnerable to cyber attack. Just thinking about if we
Yeah,
end up with something that knocks those
yeah,
out.
sure,
Are you able to talk
sure.
to that at all?
You know, ENSN, their systems are separate from ours. So, our data are fed in by multiple ways. They come back to us through radio telemetry. They come back to us through cell modems. They come back to us through satellite. Um, the USGS takes that kind of stuff pretty seriously. So we've got a lot of, kind of firewalls and a lot of protections up. Obviously nothing is 100% foolproof, but we do take that kind of situation very seriously, and we do our best to try to protect it, and we try to have as much redundancy in our telemetry pathways as we can. So if one particular side goes down, we can still get data out via a different type of telemetry path.
Hope that answers the question, and happy to hear that they're very redundant. We had a question from Crystal. Can you talk at all about the potential for an eruption at the axial seamount? This is about
Yeah,
300 miles offshore. Yeah.
right. That's a bit out of our lane. That's actually the purview of NOAA. They have their station down in Newport. Um, the potential is certainly there. I think this is they've got a long track record of monitoring that volcano, and they've been pretty good about they've got lots of instrumentation out there. They've been pretty good about learning what signals indicate that that volcano is gradually building toward an eruption. And I believe they've put out some information, kind of forecasting that possibly sometime in 2025 that volcano may erupt. But really, they're the ones to really get the information from. We don't worry too much about the offshore volcanoes. We're just focused on the onshore.
Thank you for that. All right, another tough one coming from state government to federal government. Are people just smart enough to not build in areas where there's lava flows or lahars? This one came from Gail as well.
Well, I mean, people are attracted to the beauty of the area, and people are going to build. I mean, you can ask the same question about floods and building on floodplains. So, you know, putting it into perspective, right? I mean, we get a couple eruptions per century somewhere in the Cascades. So more likely than not, somebody's going to live in a community their entire life and not be affected by the volcano. But there's always the possibility. And so we do our best to provide emergency managers, land use managers with the information they need about what the possible hazards are, try to give you some insights on kind of what's the probability of this kind of an event happening in any kind of given year. And then, hopefully that's the actionable information we can give. And then it's kind of up to, the governing authorities as to how they want to use that information.
Yeah, thank you very much for that. I always like to emphasize too when it comes to like lava flows and pyroclastic flows, a lot of those are only going to happen within the national park boundary, pretty much, which is less likely people will be living there. Less
Right. And
likely.
yeah, and I mean, as I mentioned, our volcanoes are pretty remote. So that's that's got what we got going for us. I mean, like I said, to the west of the Cascades, it's these big lahars that can move many, many tens of miles down valley that are the biggest hazard to communities to the west. And then communities to the east, it's going to be ashfall, but those are generally not going to be life-threatening. It's going to be a big nuisance, but not necessarily life-threatening. So the lahars, on the other hand, I mean, they can be life-threatening. And hopefully we are able to give sufficient information to authorities to get warnings out. Like I said, next time a volcano goes into unrest, lahars are going to be on people's radar from the get-go.
As they should be. Okay, we got a couple more while we have a couple minutes. Let's see. Gail also wanted to know, weather predictions don't seem to be accurate. So how accurate can our volcano forecasts be?
Okay, well, you know, we don't necessarily predict. We try to give our best guess as to a forecast of what the volcano can do. But, there's some caveats to that because we can have the best instrumentation out there. The volcano can be ramping up, lots of unrest. Our best guess is it's going to lead to an eruption, and then the volcano can kind of plateau at a very high level of unrest and quiet down. It may plateau at a high level of unrest for some period of weeks, maybe even months, and then escalate up to an eruption. So every volcano has its own personality, and we do our best to interpret the signals and provide information. But there's always surprises, and we can't necessarily, forecast on anything. We can probably forecast over fairly short term, maybe a matter of days, that there's a good chance that the volcano is going to erupt. But when things are in a high state of unrest, the volcano has its own personality, and it could erupt or it could stall, and that's a really tough one to try to figure out.
Okay. Um, we have one more pretty interesting one here, but it depends on how familiar you are with Jules Verne's work. Geologically, how accurate is Journey to the Center of the Earth? This is another good Gale
Yeah.
question.
Well, I was over on I can't pronounce the name of the peninsula in Iceland, but I've been to that peninsula, which is apparently where the book was set. That was his entrance to the journey of the center of the earth. I think it's a great, entertaining read. But if you want really accurate information, come talk to us.
Well, that sounds excellent. And with that, there's a lot of good questions here, and would like to remind everybody that later in this month, on the 15th from 11 to 1, we will also have a Reddit Ask Me Anything where you can ask any of these questions. We'll have a few USGS scientists there and some people from EMD. And yeah, it'll be a really good opportunity to learn a little bit more and maybe ask those wild volcano questions. But meanwhile, let's just thank you, John. Thank you for coming and talking to us today and giving us a little more education about the volcanoes in our area. Much appreciated. And
Sure.
thank
And
you, everybody, for listening.
yeah, and I'll encourage people, if you're in the area May 10th, come visit us for our open house and definitely participate in the Ask Me Anything on Reddit.
Yeah, if you've never been down to Cascades Volcano Observatory, it's a really excellent building full of good people. So
All right. Thank you, Brian.
thank you very much, everybody. We'll let you get back to your day.